Okay, today we're going to get through the rest of Unit 5, and we're going to start with Dalton's law of partial pressures. So for partial pressures, simply states that for a mixture of gases, the total pressure is equal to the sum of all of the parts. Okay, so pressure total is pressure 1 plus pressure 2 plus pressure 3, and you also can manipulate the ideal gas law to go between the total pressure and the total moles, if you know the temperature and the volume. And this is just a schematic, another visual that shows that your pressure total here is 10.1. You can get that by adding them together. Also that the moles are cumulative as well. So there's a couple of different ways that you can do some of these calculations. Now let's go right to a sample here. You've got 47 liters of helium, 12 liters of O2 at 25 degrees Celsius and 1 atm were pumped into a tank with a volume of 5.0 liters. This is obviously related to scuba diving, which is where a lot of gas law application comes in. We want to figure out the partial pressure of each gas and the total pressure in the tank. Okay, so to find the moles of each gas, we're going to use the ideal gas law. All right, plug and chug here. We convert to Kelvin. We get 1.9 moles for our helium and 0.49 for our O2. Okay, simple plug and chug here. So we've got our moles. Now we can find the new pressure of each gas, which is going to be 9.3 atms, 2.4 atms, add them together to 11.7, or if we knew the total moles, we also could have plugged that into PV equals nRT and gotten exactly the same answer. Now just as a reminder here, sig figs are different when you're adding. Remember, it's the fewest number of decimal places, so we still write 11.7 to include that one decimal place. So there's your sig fig reminder. Alright, now with partial pressure, it also shows the identities of the gases really do not matter, just the number of moles. So for an ideal gas, the size of the gas molecule is not necessarily important. And remember, an ideal gas is really high temperature, really low pressure. So because those molecules are so important, we're not even worried about the intermolecular forces. And those are things that would change with the identity of the gas typically. So we kind of ignore this to make it easier to focus on. Now mole fraction is something new. Mole fraction is just exactly what it says, the fraction or the percentage of the moles for each one. Also, for mole fraction, sorry this is wrong page-wise here, you have it right on your notes. Look on page 209, 5.16 and 5.17. But this is just another reflection mathematically that shows you the relationships between pressure and moles. And these are really just another way to kind of find percentage, so it's really not that much of a leap. Okay, water displacement. We're going to do a lab with this, and we can use water displacement to figure out the pressure of a substance, because when gas is collected using water displacement, I believe we'll use magnesium and hydrochloric acid. We're going to collect the hydrogen gas up top here, and you also have water vapor. So if you know the pressure of the water vapor, you subtract it from the total, then what's left is going to be your pressure of hydrogen. And so we'll do that lab here in next week or so. Now here's another sample. Oxygen produced by the reaction below was collected by displacement at 22 degrees Celsius. Now when you know, actually it's going to tell us here, at a total of total pressure of 754 torr. The volume of gas collected was 0.650 liters. Vapor pressure of the water is 22 degrees Celsius is 21 torr. This is something that you'd be able to find, or that you would be given what the pressure of the water is at certain temperatures. You want to know the partial pressure of the O2 as well as the mass, a little stoichiometry, of the KClO3 that was decomposed. So again, since we're doing stoichiometry, we need a balanced chemical reaction. So there's our balanced chemical reaction. We decomp into potassium chloride as well as oxygen gas, and the oxygen gas is what we collect by water displacement. And the lab really helps conceptualize this stuff. Okay, partial pressure of the O2 is simply subtracting here's the pressure of the water. We've manipulated things here. Here's your pressure total. The pressure of the gas we're looking for is O2, so it's going to be 733 torr. To find the number of moles, all we got to do is use the ideal gas law. Okay, we plug and chug. They went ahead and did their ATM conversion in the problem. That's fine. Most of you guys probably would have done it ahead of time up here, probably, where you would have taken 1 ATM, divided it by 760, but either spot. And we get 2.59 times 10 to the negative second moles of oxygen. Now at this point, we got to do stoichiometry. You could take this right into the chart. I'm going to show you dimensional analysis, but you had to figure out first the moles of potassium of the original compound by using the mole ratio. Again, you very easily could have at this point done moles, change, and X, and actually taken it all the way up to grams, out of space here. But you would have done the same thing. You would have used the mole ratio, you then would have used the molar mass to get to 2.12 grams of our original compound that was decomposed. Again, upon initial presentation, some of us may have gone, oh, do I know what I'm doing? And the answer is yes, you do. You just got to put some things together. Okay, kinetic molecular theory. A little chance to enjoy the bubbles. I stole these from someone else, so I can't take any credit for them. But okay, kinetic molecular theory, we've learned before, is a model. A theory really actually is the explanation, and we kind of do that as a model. And we learned these last year, and these are the same main ideas. Some things are a little different. One, the volume of particles is assumed to be 0, meaning that the particles are really, 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 really small. That's all we're talking about here. Particles are in constant rapid motion. They exert no forces on each other, no attraction or repulsion, and kinetic energy is directly proportional to Kelvin temperature, which, as we all remember, increase the kinetic energy, you increase the temperature. The other thing we added last year, which kind of goes along here with number 3, is that all collisions are elastic, meaning they don't lose energy. It's just transferred between them. And I've got a quick video that we'll watch in class that's much better animation than mine that exemplifies this. Okay, so this is just showing you the explanations for Boyle's law. Well, it's bad highlighting. Decrease in volume means the particles will hit each other more often and it will cause the pressure to increase. Okay, I think most of us are pretty good with these. Gay-Lussac's again is pressure and temperature. If we increase the speed of the particles, the temperature will increase, and so we get increased pressure. So these guys are directly related. Remember, we would have our PTV cards too that we could use, and if we increase pressure, increase temperature, they're going to go the same. However you want to remember it. Volume and temperature are examined in Charles's law. Again, if you increase the temperature, it's going to increase the speed, so you also will increase the pressure. Excuse me. I'm sorry. If you want to keep pressure constant, the volume must increase. This one is looking at the difference between, or the relationship between volume and temperature. Avogadro's law, this one seems really easy to me, but if you increase the number of gas molecules, then you're going to have more moles. And again, to keep the pressure constant, the volume must increase. So these slides just kind of take into account the other ones and how we have to keep them constant. Okay, Dalton's law, kinetic molecular theory, assumes that all particles are independent of each other, and so that's how we can explain Dalton's law. Whoa, fancy. Okay, temperature. This is the math behind why temperature and kinetic energy are directly related. So it's a sign of the random motions or the randomness of gas particles, and so this is just kind of the math behind it. Again, the only thing you would need here is the ideal gas law. Sorry, the ideal gas constant. Higher temperature means greater motion. Another thing that's new is called the root mean square velocity, which allows us to compare how fast different gas particles move. This is a biggie. They have to be in kilograms per mole. And also here, when you use the R value, and I'm going to show you in a minute, this is the other R value because you're going to deal with motion and joules, and that's the way I remember it, because when you see why, you'll see why it gets canceled out here in just a second. Okay. Let's see here. Almost there. This just shows you as the temperature increases, the average velocity also increases, and the spread of the velocity will increase. Okay, so here you have 273 Kelvin. Most of the velocities fall into a small range. As you increase your temperatures, you get a broader range because there's just more options. So it's just showing you that the spread of the velocity increases, and that's why it's just another way to kind of compare it in another relationship. All right, here's the example I was telling you about. Root mean square velocity for atoms in a sample of helium. Okay, here is your different R. It's the joules, moles, Kelvin. Okay, we're at 25 degrees Celsius, and all you had to do here, make sure that it is kilograms per mole. So all you have to do is take your molar mass and divide it by 1,000 to make sure that it's kilograms per mole. And then our units are 1.36 times 10 to the third meters per second. Okay, so it's just a way of comparing how fast different gas particles move. All right, last but not least, we got to talk about effusion and diffusion. Effusion is kind of this random, I say that a lot, don't I? Random property where gases can pass through a very small hole. And the only time this really comes in is comparing them that we're going to see it. So if you have all these gas particles, how fast will they pass through a small hole, which is effusion. Diffusion is the random mixing of particles. They will continue to mix until they're evenly distributed. This is the math behind effusion. It's called Graham's law. I realize they're opposite from each other. I didn't make a mistake for once. Effusion rates depend directly on the averaged velocity, and the fact that they are directly related is kind of math-wise why they have to be opposite. So the faster they're moving, the more likely they are to go through the hole. I think that's pretty self-obvious. And same thing with the molar mass. The smaller they are, the more likely they are to go through the hole as well. And this is just looking at the rates of hydrogen and the rates of oxygen. And this is just simply that H2 effuses 4 times faster than oxygen. Okay, because since they're smaller, they're going to be moving faster, and they're also just smaller parts and pieces. This is just showing you how they mix. This is more of a diffusion over here, and then the smaller one is effusion over here. All right, last but not least, here's our caveat, or a little asterisk here. We know ideal gases, ideally, are going to happen with high temperature and low pressure. Particle size is so small compared to the space between them, and the interactions are insignificant. That means no forces of attraction or intermolecular forces. But real gases, non-ideal conditions are very low temperature and very high pressure. So there are going to be intermolecular attractions, and it's going to trump all the stuff that we've been telling you about. And it's really just to make sure that you understand that this is really how it happens. It doesn't change our math. It's just if you were asked to compare them, the differences would be they're much closer. So you get more of these forces, and this happens at low temperature and high pressure. Okay, there's the rest of Unit 5. I hope that helps, and we'll do some problems.